Hello everyone, this is Renjie again. Today, we are going to discuss some very important concepts of engineering mathematics. Specifically, we are going to review Taylor series and expand Taylor series to introduce Newton-Raphson method, which is a very important method on doing engineering simulations. And we are going to solve a nonlinear equation using the Newton-Raphson equations. Newton-Raphson method, I'm sorry. Let's get started. So again, after you opening this Colab file from GitHub, you always need to copy to your own Google Drive. So in this way, you won't lose any modification you made on this file. Okay, so what is Taylor series? Taylor series is about making a non-polynomial function, most of times nonlinear, and find polynomials from this function by expanded to be polynomial terms. For example, here is order of 1 polynomial, order of 2 polynomial. The reason we want to convert a function into polynomials is because it is much easier to deal with polynomials than other nonlinear functions because they are very easy to compute, take derivative, and integrate. And also because sometimes this value, this Rx minus a value is small, we can trim this expansion to use only part of it, and we will see that in the following section. Let's use Taylor series on a real example. This example is about potential energy of a simple pendulum. So we want to have to know the potential energy of this pendulum at a certain degree. So when you do a very simple free body diagram, you'll find out that this potential is proportional to h, which is this formula, r times 1 minus cosine theta. But we have a cosine function here, so this equation becomes kind of awkward and not very easy to compute. So let's do Taylor series on this cosine function around maybe a equal to 0. In this case, we can simplify the equation to be this. Compared to cosine theta, this is much smaller, much simpler, and it should be approximate to the real answer when theta is small, which is around 0. So let's do this. The first thing we need to do is to get the real equation. So it's 1 minus cosine x. So again, I'm using NumPy, the NumPy library to do the cosine computation. But after using Taylor series, we don't need this NumPy library again. Then we do the first order approximation for this cosine function. So let's do it. So it's here. So it's r times theta squared over 2, and we assume that r is 1. So then this becomes theta squared over 2. So let's do theta squared over 2. And because we want to have a list of these answers, we can do either by for loop for I in maybe range of x. So I in x. So let's compute this h equal to I power of square power i's power over 2. Then we have maybe z equal to an empty list, then we add this to z. Okay. So let's make a plot. As you can see, because this is a approximate function, it works pretty well when theta is close to the origin we are expanding, which is equal to 0. But when we are moving away from this expanding point, the error becomes larger. And there's another way for us to write this kind of list, simple for loop in a list in Python, that is to do list comprehension. So it's inside a list because we want to compute every element in the list, so we can do it in this way. I power 2 over 2. Okay, so this time we want to have for I in X. So using this notation, it is much simpler compare this full version of for loop. So for this list can be read as for I in X. So I want to compute this and use it as one element inside this empty list, which is C. Okay, then we can do the same thing here. See, the results is the same as we have computed before. We can add one more order term to have a better approximation. So let's add a second term here. Because we have multiple terms here, so it's better to write an equation or function, and then we can use this function to do a list comprehension. So in this way, it's easy to read and easy to modify. And let's do this. It's written to first, this is the first order, which is here. Then let's do the second order, which is x to the power of 4, which is here, then over a factorial of 4. Then the factorial is called from the math library. Then we can do the same thing here using list comprehension. But in this time, we are calling the approximate function instead of a simple equation to compute for the second order approximation of cosine function. Let's do this. Okay, as you can see, when we add another term, the approximation is more accurate and the error is small when at 0, when the theta is close to the expanding point 0. Then this is a function we have created for you to play with. Let's execute this. So basically it's an interactive cell, so you can play with the number of orders you want to have and to see how accurate this approximation is. So let's do maybe the last one, order of 6. So in order of 6, when theta is around this range, it's almost the same. So the approximation is pretty accurate. But when when terms is smaller, the order is smaller. For example, when order is 3, and it diverges when the theta is bigger than from 2. Okay, that's all for the concept of Taylor series. Basically, you can use Taylor series and truncate the Taylor series to make a simple approximation of a nonlinear function around some points. As long as you are not very far from this point, the approximation should be accurate. Then we are going to use Taylor series to introduce this Newton-Raphson method, and we are going to use Newton-Raphson method to solve a nonlinear equation. The nonlinear equation we are going to solve is based on the sliding block problem from day 2. If you don't remember that problem, you may want to go back to day 2 to take a look at it. So in day 2, we introduce sliding blocks and we use for loops to find the optimal angle of pulling that block. In day 3, we continued this problem, but this time we are trying to find the angle, the pulling angle, when force and friction and other parameters are given. We used a simple section method, but in this class, we are going to teach you how to use Newton-Raphson to have a better approximation method to solve this equation on finding the pulling angle theta. Okay, so the force is equal to this equation, as we always know from the previous 2 classes. Then we can have a new function which is defined as here. So basically, it's just the estimated force. So it's a force based on this theta minus the known force, which is 17.5. So this is our guessing error. So our goal is to find the theta that makes this function to be 0. When this function is 0, which means the guessing term is equal to the actual term, so the theta corresponding to the guessing term will be the solution for this theta. So how can we do that? We are going to use Newton-Raphson method. To use Newton-Raphson method, we do a Taylor series on this equation. This Taylor series can be written in this way. So assume that we have another theta, which is the new theta, new guessing points from the previous one. And we want to know what is this new guessing point from the previous one. So we expand the equation based on the previous one or the initial guess point. Then we take a Taylor series about this optimization function or objective function. Then we'll have the first term, second term. Because we are going to do a demonstration, so we only considering the first derivative term. So we are going to omit the higher order terms here. We'll have this equation, and the updating step of this error term will be in this form. So when we add this updating step with the previous function, with the previous step, we're going to have the new guessing points, which is theta n plus 1, which is listed as following. And so the problem for this is that we need to have the gradient. And if we know the gradient, then we have all the elements. Then we can use the above equation to iteratively solve theta from the initial guess point, theta 0. And we stop the iteration when this error term becomes very small compared to a predefined tolerance. So let's do some basic calculus around this objective function. Then we can reach to this first order gradient. And we are going to use Taylor series for both theta, cosine theta, and sine theta to make everything to be consistent. So let's write it up in Python. So we have provided approximate cosine and the approximate sign in this cell. All we need to do is to define the objective function here, which is defined by the equation here. So let's just write it down. It's mu times weight over cosine sine. Notice that we are going to use the approximate cosine sine because we are going to use first order Taylor approximation. So we want to have everything to be consistent. Then next we are going to define the gradient function, which is defined here. So again, we are just type everything out to have this function, which is here. Then let's use Newton-Raphson to solve for the Pauling angle theta from all these question settings. Do that. I recall that as we discussed here, Newton-Raphson is a iterative method. So let's iterate it one by one from the initial guess. So for I in range, so that's number of steps we can have. Maybe we want to have a very large maximum number of steps. So it is guaranteed that this equation, this Newton-Raphson method will converge. First thing we are going to have is to compute for this term, j over the gradient. So let's just compute it. So it's h equal to j function Gfn over x. X is the initial guessing point. Then it's over this function. Then we are going to update the theta using this equation. So the theta will be updated as x equal to x minus h. Then if this h is very small, this difference is very small, maybe to 0.01, then we just return x and I. So x is the theta we have from Newton-Raphson, and I is the number of steps taken. Then we assume the initial point is given as this value, and mu and weight is given by this. Then let's compute the final force, which is just this function plus 17.5. Then the absolute error will be final force minus 17.5, and the relative error is given by the error over force times 100. Then let's print the final result. So after 3 iterations, we reach to this angle and gives us this force, and the absolute error is very, very small. It's to the magnitude of 10 to the minus 10. And the relative error is also small. It's also in the order of 10 to the minus 10%. So that's all for today's discussion. Today, we introduced our reviewed Taylor series and Taylor series approximations. Based on Taylor series, we introduce the Newton-Raphson method and gave an example about how to use Newton-Raphson method to solve a nonlinear equation. That's all for today. Thanks for your patience.